So I'm assuming most people are familiar with the basic idea of trying to average opinion polls. We have lots of opinion polls from lots of different opinion pollsters, and they come out sporadically, sometimes more frequently than others, and different pollsters have different estimates of vote intention, and the pollsters differ systematically to some extent. And we want to do this for two main reasons. One is we want to understand how public opinion is changing over time and what happened and why the parties went up and down when they did. And so the time series analysis is important. I'm also involved in running a forecast for the next British general election. So my particular immediate concern is trying to get this right, but trying to also get the current estimate of current British vote intention right, and make sure it's right when we're very close to the election. And actually these two aims are not always concordant, as I am going to essentially try and argue and come back to towards the end. I'm looking at sort of two main kinds of methods, and actually looking informally at these two different kinds of methods. There's a kind of broad class of informal methods where you somehow just try and calculate some kind of straight average of polls, and you make some decisions about which polls to average and how far back you want to go. So, as an example here, I've given you what John Curtis did for the Scottish referendum. He just took the last 6 polls that were published and averaged them. When he does talks on British vote intention, he has a method of taking the regular monthly polls, and so when he wants a monthly time series, he'll just take one poll from each pollster that was published around about a particular time of each month. That's when they're all publishing polls, and so they get a fairly consistent measure over time like that. Anthony Wells, who runs the UK Polling Report website, who's a wonderful commentator on British polling and polling in general, he has a reluctantly, apparently, generated a polling average, which weights by time, so it penalises polls the older they are. He has a bit of reputation, methodology, weighting. He will only take effectively the last 3 or 4 polls from each pollster, so as you'll see, it doesn't end up being too dominated by 1 or 2 pollsters. And effectively only the last 20 polls over the last 20 days. He has sample size weighting as well. So that on one level seems very sensible and good to me, though some of the decisions are quite arbitrary. And then there's a more sort of political science tradition of fitting dynamic latent variable models and similar, and not fully going to try and go into all the details of all the different attempts and particular formulations of these models. But they essentially are statistical models of public opinion. They say public opinion is something that we're not directly measuring. What we observe are polls, and polls have sampling variation associated with the sample size that we have to model, and there are house effects that we have to model. And there are various assumptions about how these house effects are modelled and what we do with them. Typically, and maybe somebody can correct me if I'm wrong, the house effects are assumed to be stable over the cycle. And then there are questions about anchoring. So in the Jackman 2005 paper I just cited, he was doing a post-election analysis and he anchored to the eventual election result. He advises in real time that you obviously can't anchor to the future election result. You have to, he advises you to anchor to the estimates of the house effects of the previous election, and that's what I think Mark Pickup and his colleagues are doing with the UK Polling Observatory estimate of public opinion that some of you might have seen. So they essentially use house effects in 2010. But what we also know from work I've done with him and others is that house effects in 2010 were very different from house effects in 2005, and especially given the changes in public opinion since 2010, and the patterns of the polls that I'm going to show you, there are lots of reasons to believe that the house effects are going to be changing and be different in 2015. There's an easier assumption to make is that there's no industry bias, but historically there has traditionally been a fairly stable pattern of industry bias, with the Conservatives typically underestimated and Labour typically overestimated. Who knows whether that's going to happen again, but it seems to me odd to ignore it. But you could say there's no industry bias and then peg to the median or the mean pollster, which is what I think electionforecast.co.uk, and Ben Hollidale and his colleagues do, which is a useful assumption. The problem is, as I put essentially at the bottom of this slide, as I'm starting to argue, house effects can vary, and we don't know what they are, and we don't know what the industry bias is going to be, and they might all change over time. But you also want to estimate changing public opinion over time. You're going to end up with an identification problem, particularly if this is all allowed to be as arbitrary as you like. So what I'm trying to do now for the rest of the talk is look through the data to see to what extent can we kind of just through techniques of exploratory data analysis identify whether it's the public opinion changing or the house effects changing, and then start thinking about what the optimal strategy might be for averaging polls in real time as we approach the election. So I've taken the polling data, the headline published polling figures, which is a bit different. I just learned over lunchtime from Ben what their team are doing, which is much more pure to the actual responses. I'm looking at the house published figures with all their adjustments, and this table shows you just the frequencies of the number of polls for each pollster since May 2010, and you can see that nearly 2/3 of all the polls were by YouGov, who have done daily polls apart from weekends, and they essentially never end their polls on Saturday and Sunday. And then you've got another few pollsters who are doing serious amounts. Some pollsters like ICM and Ipsos Mori, traditional pollsters, who have been doing basically one poll regularly every month. Those are big traditional pollsters who've been doing election polling for a long time. And then you've got some that are sort of relatively newcomers and kicking in with more frequent stuff recently. So you can see Ashcroft did 29 polls in 2014, but not much before that. And so we're going to have to deal with this sort of lopsided mix of polls and pollsters, and going back to sort of issues of dynamics. Obviously, it's going to be interesting if you ever want to do something detailed. YouGov provide the most detail on dynamics, but then the question is, are they telling us the right pattern dynamics? But I'm going to be more focused on changes in share. So I'm going to show you a series of graphs now which just show you the line plots for the different pollsters for each different party. This one's for the Conservatives, and what you can see there is that in terms of the big pattern of change, they are roughly telling us the same thing with a bit of noise, and things seem to be getting a bit noisier towards the end of 2014. The house effects here for Labour are rather stronger. You've got, I think it's opinion, noticeably lower for Labour, particularly towards the beginning of the cycle. But again, very broadly, they're showing us similar patterns of change. The Liberal Democrats have a very noticeable outlier with ICM, who we know are doing what they call a spiral of silence adjustment, so that they are adjusting non-respondents' don't knows to their previous vote, and we know the Liberal Democrat vote was much higher at the last general elections, so that's why ICM are coming up with much higher Liberal Democrat figures, but still the same pattern of change, which is actually fairly flat for most of the period after the initial fall. UKIP have at the party where the pollsters disagree most in terms of where they're at. Some of the gaps here you'll see are huge if you follow this issue in the US. Imagine if the US pollsters differ by 10, 15 points on where the Republicans and Democrats were. Maybe I'm wrong, but that would be nearly all the variance there is. And you've got some very clear signs of Salvation being the pollster with the very highest UKIP share, almost entirely consistently, and Opinion being up there as well. Meanwhile, some others are much more often near the bottom of that distribution. And then the Greens have picked up in 2014. You might be wondering why I'm bothering to show you the Greens, but that will become transparent a bit later. So the picture so far in the presentation, I would say, is that kind of broad stories. We're not seeing anything serious, so it suggests they're all pretty broadly the same pattern change, and there's some stable, clearly a lot of stability to the House effect, if not very clearly. So both of those things suggest that a classic state space latent variable model should work well, but those graphs are not very well designed for picking out changes in House effects. And one of the virtues of the YouGov data being so frequent, particularly if you interpolate for those odd missing days, is you could just measure everything against YouGov for all the other pollsters. And that's what these graphs do. And because these are all lower smoothers, with slightly different degrees of smoothing, I'll admit. So there are enough populist polls in 2014 to look at it a bit more carefully. There aren't so much for the others, and some of these graphs, the flatness is driven by sparseness as much as anything else. But what you can seem to see here, particularly populist, is if the House effects were entirely stable, all these lines would be flat, and they're not flat. You can see YouGov on 0 in the middle. There's a bit of a trend upwards for populist, and again, some funny stuff going on with Labour for populist, and also other pollsters, a collection of other pollsters, all showing a trend in the second half of 2014 relative to YouGov, suggesting that actually the YouGov House effect is changing, particularly relative to the rest of the industry. The Liberal Democrats, you see, exert much more stability with though some waves that seem a bit inexplicable. You see a mixture for UKIP of stability and odd change. You can see that some of the downward stuff that populists picking up is echoed in Ashcroft. Why particularly those two would go together, I'm not sure. But then the Greens have got the most striking story of YouGov differing in terms of its pattern of change from every other pollster there at the end of 2014. YouGov basically had the lowest Green share of the vote for most of the cycle, and then in the second half of 2014, YouGov showed the biggest increase in the Greens, and the others showed a much smaller increase in the Greens, which is why the House effect changes with this particular pattern. So it does seem to be a mixture of sort of stability and change for the House effect. And what's more, if you start trying to think about theories of House effects, you might think the most natural thing is structural breaks. If somebody changes their methodology, it might push one particular party up for a bit. But there's not much sign that this is following clear structural breaks, especially not linked to any announcements of methodology differences. The other thing to think about here is that we have some side information We know that these newer internet pollsters with large UKIP shares didn't do very well at estimating UKIP at the Euros, so we might actually deliberately know that those are likely to be wrong and believe the lower estimates for UKIP more than we believe the high ones, particularly with observation and opinion. ICM, it's a bit of a puzzle to know whether we should believe ICM or the rest of the industry at this stage, and whether that will continue as we approach the election. And the Euros are no help here, because ICM actually were in the middle and had a relatively low forecast for the Lib Dems. They were spot on, which ICM have basically the best substantial reputational situation in terms of best record on predicting elections. There are actually substantive methodological reasons to expect why the House effects might change over time. So I don't think this is all just spurious noise. There's enough data here and reasons here, and the fact that YouGov weight to party ID, Green party ID is changing over time. YouGov are weighting to the party ID at the time of joining the panel, and that might change things. The real clincher for me as a forecaster is fear of what happened in Scotland. You might know that the Scottish polls had massive House effects up to 2 weeks, and then 2 or 3 pollsters moved up to join the ones that already had high yes shares of the vote. The House effects disappeared in the last 2 weeks of the campaign. If you had had a model with House effects that were stable, you would have ended up predicting a yes vote. And what's more strikingly, you would have ended up predicting outside the range of the observations of the data, which you don't really want to do, or I think you don't really want to do it, but you really would find it hard to explain to the public why your estimate for the Liberal Democrats is higher than any recent poll rating for the Liberal Democrats, or Greens, or whatever. Actually, that would be a risk for the Greens in this recent story. Up to the end of 2009, you might end up predicting a higher Green share of the vote than any pollster has done, because of this change with YouGov. So, I'm sorry, I'm running out of time, or probably have run out of time. I think you can see where my argument is going. All of this makes me quite worried about fitting House effects and trying to model House effects effectively, and so much so that I am drawn towards sort of more informal polling average, and the more I look at this, the more I wonder whether Anthony Wells's approach, if not his exact reputational weighting, which I'm still sort of thinking about, but will always end up being rather arbitrary in terms of judgment calls. I wonder whether his approach is fundamentally the right approach, even if, so for getting good, relatively robust and risk-free estimates of current public opinion, even if they're not the ideal for post-match analysis, because they will tend to vary a bit due to compositional factors. For post-match, post-election analysis, where we're trying to estimate the best time series for understanding the campaign dynamics, you probably do want to go back to a proper statistical model. I'll end up there. Thank you.
This is a paper I'm working on with Fabio Wasserfallen. We started working on this because we were in a substantive project using multi-level regression with post-stratification to get estimates on different policies in the Swiss cantons. So we wanted to know in which cantons do certain policies have higher or lower support among the population. And one thing that we realized quickly was that we had a couple of good variables in the individual level survey, but we couldn't use those variables because they were not part of the census, which is a requirement when you're using MRP. So that's where the motivation for this paper comes from. So for those who have maybe forgotten or not seen or do not know what MRP is, what it is it's one possibility for you to take a national survey with maybe, let's say, 1,000 people, and then you want to generate out of that estimates for subnational units. And so goes back to Gelman and Little, wasn't really used, and then Slacks and Phillips that then start applying it on a bunch of substantive issues, and then also show that it performs better than other standards. What were other standards? Well, one very simple way is that you can just say, well, I'm going to take my national survey, and I'm just going to look at how many people say yes in a specific question from a specific state, and then that would be your estimate. That would be like disaggregation. Probably not the best you could do, but it's one of the things that is often used as like a benchmark to show how much better you can do when you use MRT. The problem, or the cost, because this is of course not coming for free, is that you need to have very precise census information. So all the data you're going to use in your hierarchical model on the survey data, the individual level variables, you need the equivalent survey information. So I need to know, for example, in Nevada, how many white men I have that have a high school degree and are between 30 and 44 years old. And so our problem originally was that we had variables like party ID that were not part of the census, but were very, very strong predictors for attitudes. And so certain frustration that we can't use them. So the way you use MRT is you start with a survey. It's often 1,000. We have some cases here where we're almost down to 500 because there's so many people that do not respond to a specific question. In the second step, you're going to use your survey data and you're going to estimate the hierarchical binary model. And this is just a very stylized, simple example. But the basic idea is that you're going to introduce random effects for different groups. So sex is easy, education might be like a 2, 3, or 4 group variable. And then eventually you're also going to have a random effect over constituencies. Then we can think in terms of ideal types. So if we have here now sex and education, let's say there's just low education and high education, then what I get is 4 different ideal types. I get men with low education, with high education, women with low education, high education. So the prediction for any specific combination in constituency C, so for example for a woman with a lot of education, is just going to be the realization of the random effect for women plus the realization of the random effect for higher educated people plus the realization of the random effect for that constituency. And that gives me the predicted support for that ideal type. And then in the last step, and that's where the post-stratification comes in, is we're going to weigh each of these the predicted support of an ideal type. We're going to weigh it by the relative frequency in that constituency. So thereby you're taking into account that you actually have knowledge and know that in certain areas you have more better educated people or less. Now, the problem is that when you do that, then you actually need the joint distribution, meaning you need to know what is inside here in the cell. So you need to know the combination of low and gender, and it's not enough to just have the marginal distribution. The reason for that is that imagine for a second you wouldn't use a probit model in the hierarchical modeling step, in step 2. Well, then you could just go and average over the random effects, and you wouldn't have to bother about the ideal types. It would be enough that you would just have the marginal information, and then you could just get the average person in a district. The problem why this is not working is because we have this phi, we have the link function, whether it's a probit or a logit model. In both cases, the first derivative is non-constant, meaning the random effect you add, like the realization, for example, for being a woman, is going to have a different effect for a higher educated person or a lower educated person on the observed scale, on the predicted probabilities. So that's why we're forced to have that. The very first thing we tried to do was actually to not use logit or a probit, but to just run a linear model, but that doesn't work out that well. The second thing then is that we say, so what happens if we actually, and this is the most simple way to come up with an alternative joint, if we just assume independence and we multiply the marginals together and create a synthetic joint distribution. So we know that our post-stratification data is wrong to a certain extent because we assume orthogonality. That's not necessarily the case. So you see here in this example, we would have 40%. Over here, we would think that we have 36. But no, we're never going to be counting not enough men per constituency or not enough highly educated people per constituency. It's just that we get the combinations wrong. And so the huge advantage of this is that you can now use any variable for which you can get a marginal distribution. And that's usually something that is fairly easy to get your hands on. Now, what that means is that you can suddenly use MRP in a lot of situations where you could not use it before. The lowest degree on, or the lowest level in which you can get census information in India, you're only going to get it as marginals because it's data protection. The state is not going to give you joints. So there's no MRP happening there. Well, if you use some synthetic joint, then you can actually use it. Switzerland might not surprise you given the reputation of that country is not going to give you income data. Well, we know income is a very powerful predictor for a lot of policy preferences, but you're not going to be using income with MRP. In the US, it's party ID. It's a powerful predictor for a lot of things. You cannot use party ID because you're not going to get it from the census fact finder. So in all these cases, this extension of MRP might allow you to come up with better estimates, although you're basing it on a slightly off joint distribution. So accepting a tiny mistake in the beginning might eventually lead, nevertheless, to much better estimates. And so what I'm going to show you is I'm not going to show the Monte Carlo simulation. I'm just going to show you an application where we're using the same data, and you're going to see that there's virtually no difference between the two results. And then I'm going to exploit the fact that we can include more information when we rely on a synthetic joint distribution. I'm going to show you how we perform better than if we would have not included the additional information. And that's based on data from Switzerland and from the US. So what you have on the y-axis here is the mean squared error over 26 cantons. And every single dot represents one vote in Switzerland in the last 20 years. And so we have survey data for that. And then the red dots show you the mean squared error when you use the true joint distribution, and the blue dots, they show you the mean squared error when you use a synthetic joint distribution. You might be wondering where the blue dots are. Well, they're actually hidden under the red ones. So it's only when we zoom in to this part here that you see that down here some blue points are hidden. So there's virtually no difference in terms of mean squared error from using the true joint or the synthetic joint distribution. Again, for every canton, we're having the exact right number of highly educated people, of women, of people living in the countryside or not. It's just that we got the combination sometimes a little bit wrong with the synthetic joint distribution. And it virtually doesn't matter. To get a sense of the scale of the error, this dashed gray line is showing you the mean squared error if you would have used this aggregation. Now let's go and use more data. So now we're looking at 4 specific votes coming from the populist right-wing party in Switzerland after 2007, where they lost their big leader, and they started a campaign that was essentially we against the rest. And part of that campaign were these 4 very specific votes. That's the one most of you will have heard of. So you can build churches in Switzerland. If you want to build a minaret, it's a little bit more difficult now. So what you cannot use when you use MRP is the party ID. But exactly in these votes, it was key to have a good prediction to actually know in your survey data, is this person saying that tells you that they're supporting the measure, is it somebody who identifies with that party, is a follower or not? So you can see blue dots are the ones where we actually use that and use the synthetic joint. And you see that our proportional reduction of error goes here from 30% better to up to 80% better by just adding this party information that we have. And well, some of you might not trust Swiss data. We can also go and look at an example from the US. So this is a published paper by Warshaw and Rodden, where they look at support for same-sex marriage in the US. And they do it on basis of state Senate districts for 4 or 5 states that then also had a vote, so that they can validate their survey results, their predictions with actual outcomes in those districts on that measure. And the problem they have when they use the census fact finder is they can get a lot of information, but age is not one of the variables they get for the joint distribution on those state-level Senate districts. Now, we're talking about do you support same-sex marriage? Well, actually, in this case, it's the reverse. It's actually, are you against same-sex marriage? So a high value means you're against it. You can imagine that actually knowing how old somebody is and using that in a post-ratification step is fairly important for a question like this, since we know that young people nowadays, even conservative young people, don't care too much about this issue anymore. And so they don't have that variable. We go and we take their replication data because they make everything perfectly available. We add the age marginals, which you can get as a marginal. Then we create a synthetic joint distribution, and we get our estimates again, then being the blue dots. And if we now go down here and we look at the mean squared error, you're going to see with disaggregation, the improvement from disaggregation to MRP is about the same improvement as you get again when you go from MRP to MRP with a synthetic joint distribution. So MRP is very useful and also fairly relevant, given that in comparative politics there's been such a shift to subnational studies, and one of the key variables we're often going to be needing is some kind of preference measure for different regions, and how to get at that preference measure. Well, MRP definitely is a very helpful way. There are instances, as you saw with the same-sex marriage, where you can do much better if it was possible to actually use more variables from the survey data you have that are powerful predictors. And this is one way how you could go and fruitfully use that information. There are two things we are right now working on that are not perfectly clear, and hence also not in the paper yet. One is very clear rules, or at least clearer than we have them right now, on what are situations where you can just go and use what we call MRMP, like the marginal post-stratification. What are situations where you can do that? And what are certain things you should be looking at where it gets iffy, or where you might even go as far as to say, no, I shouldn't use such a variable. So as an example for that, if the additional individual variable you want to include is one that has a very tiny variance over its random effect, well, what that means in the response level is that it actually doesn't really change your predictions too much. So probably then there's no point in including that. If it's a variable that is highly correlated with another variable you're already using, well then again, you're not going to be adding a lot of information. But then there are other questions, and it came up during a review, that what actually also matters is the average level of support. So are we looking at questions where the support is somewhere down at like 30–35%, or are we looking at questions where the support is very close to 50%? When you're around 50%, then adding on the latent something and then later subtracting it is about roughly going to have the same marginal effect. But the further you move away, the larger the difference is in absolute value of adding and subtracting a constant value on the latent. And the other is, of course, that what I said is we use a synthetic joint distribution that is just a product of the marginals. Well, that is the most extreme case, of course, of just being like, I don't know anything. There are other things we could do. We could take the survey data, we get a correlation structure in the survey data for these different individual level variables. We can then take the marginals and try to come up with a joint that reflects this correlation. So these are things we're right now thinking and working on.
Well, hello everybody. I'm interested in forecasting US presidential elections, and I'm using citizens forecasts to do so. Let me start by giving you the three key ideas behind this paper. The first one is quite simple. I want to forecast state-by-state votes, because as probably all of you know, the US presidential elections are decided by the electoral votes and not by the popular vote. The second key idea is to ask citizens to do the forecasting for me. So I will ask them, who do you think will win, and then based on that I will make a prediction. And the key driving force behind the success of this model is the wisdom of crowds, the finding that groups often predict better than the best individual in the group. And the third idea is to use and this is really where the innovation of this paper is to use a Bayesian hierarchical model for two reasons. First of all, previous research didn't account for inferential or predictive uncertainty, which is quite important in communicating the results. And secondly, the model had in a way no base for making predictions in states where nobody was interviewed, whereas the hierarchical model provides a framework for doing so. Now, let me just highlight a bit the previous research. The rule of this, or the forecasting rule, is quite simple. You just predict the candidate to win, which most citizens say will win. And this simple rule predicts surprisingly well. There has been pioneering work by Mike Louis Beck and Andrew Scalaban in the US, later with Mary Stegmaier. I myself have a paper about the UK and one about the US. It works surprisingly well about forecasting the constituencies, forecasting the national results, and you can also forecast the vote shares much better than you do with vote intentions. There's a paper by Andreas which shows that vote expectations are better predictors than vote intentions. So it works, at least in these two countries, quite well at the national level, but also at the subnational level. So you might now ask, well, why is that a much better predictor? And the question that I ask is, how can I make that even better? So the main driving force behind this is Condorcet's jury theorem, which deals with a situation where a group of people faces a binary choice task. And it has basically two statistical arguments. One is that you can vary the number of people who are in the group, which is n, and you can forecast the average probability that a person will make a correct forecast or a correct decision in a jury setting. Now, this is based on the law of large numbers. It simply says that if every member in the group has a larger than 50% chance of getting it right, and the group decides by a majority rule, if you increase the group size to infinity, well, also the probability that the group will make the correct forecast approaches unity. And this phenomenon even shows up in very small groups. So if you have, I think, on average, 60% of us would get it right if we are a group of 5, or by majority rule, we would get right about 80% of the decisions already. So that's in a way, the power of aggregation that you have in here. This also already sets the stage of how we can, in a way, improve the forecasts of this model. So here I just outline, in a way, the standard model of forecasting, and I introduce a bit of notation because it is a bit more handy than in the hierarchical version of it. So let's say that Rj is the number of people who say that the Democratic candidate will win in state J, which we observe, and then we have Nj, which is the number of total people that we interviewed and that made a forecast. So what the standard model does is just takes the raw value, which I call in this case Pj raw, which is just Rj over Nj. That's the proportion of people who say that the Democratic candidate will win in this state. And the previous research, including my own, has just then said, well, if more than half of the people say the Democratic candidate will win, we predict this candidate to win. And if more than half of the people say that the Republican candidate will win, well, we predict this candidate to win. A very fairly simple forecasting rule. However, this forecasting rule is deterministic. I mean, there's literally no uncertainty that we communicate in our forecast this way. And there are at least two sources of uncertainty that we have. And the second, in a way, area of improvement is that we have missing forecasts in state where there was nobody interviewed. So in a way, as a solution, I propose that we treat this Pj as an unknown parameter, which comes from a distribution. And there are several ways of setting this up. I just present one here, where I say, in a way, that this is comes from a hierarchical distribution. And I nest, in a way, respondents within states, and then the states also in the region. And here's one way of writing this down, is just to say that the Rj comes from a binomial distribution. We observe Rj and we observe Nj. So then, in a way, we give Pj a distribution. Then I use a logit transformation and give the Aj a hierarchical prior. I say it comes from a normal distribution, and that the mean of this distribution varies in a way by region. So anyway, it's just an empirical based estimate based on the census and census region. And then I have uninformed priors for all the other parameters that are there in the model. I estimate this model using JAX via the RJAX package in R, and just by specifying this hierarchical model without adding, in a way, additional survey information, I can easily compute the inferential uncertainty about Pj. This would just mean if I would interview the same citizens again, they would probably give me a different forecast because of measurement error or whatever. But in a way, I'm uncertain about what this PJ is that generates their responses. It's in a way an unobserved variable. The second thing is that there's predictive uncertainty. So even if I know that 70% of citizens say that the Democrats will win, well, the forecast might still be wrong. And in a way, I assume right now at the moment they might be right in 7 out of 10 cases. But I would need to account for this predictive uncertainty that comes from this model. The third advantage is that the hierarchical model allows, in a way, to create predictions based on a statistical framework, or at least on assumptions, to create predictions for state without respondents. Of course, you could randomly decide them, but I will show that this method outperforms these random decisions. So here's how this would work. For an old state, this is how the forecast would look like. First, in a way, I sample from the normal distribution of the posterior distribution of my state estimate. This is my inferential uncertainty. I do this 1,000 times, and then I plug this into basically a Bernoulli draw, and this is my predictive uncertainty, whether or not the state will then be correct or not. For a new state, basically what I will be doing, I also draw from a normal distribution, but because I do not have the posterior distribution of that state estimate, I will use the one of the region, assuming that states in a way are correlated, that are living or placed in the same region. And then again, I draw from a Bernoulli distribution to say whether or not that this forecast will actually be in favor of the Democrats. The data that I will feed into this model comes from the American National Election Survey between 1952 and 2012. In total, this gives me 11 elections where this question has been asked. And in a way, it's a real forecast because most of the interviews were done before elections, and nearly half of them were finished 4 weeks before the election. So even mostly before the election campaign really gets started, people are already very good in predicting who is going to win. And the only question I will be using is, how about here in your state, which candidate for president do you think will carry this state? And it's usually people just say a Republican or the Democrat. Now we'll use these data and these models to show, first of all, that the accuracy of the model improves at the state level and also in forecasting which candidate will win the presidency. And I will also show you some of the estimates of the uncertainty that I will be getting also at the state and at the national level. So let's start at the state level. It's just a simple prediction of who will win in this candidate, and I'm pulling all the elections together. So I have in total 558 state elections that took place in these 11 national elections. Here are the results for the standard model. You get about 60% of the states right, but unfortunately about a third of them, or about 30%, you have no prediction at all. The previous papers have shown this is already enough in a way to make a good forecast, but we can do better than that, and we can even generate predictions in state where there has been no forecast. This is what the hierarchical model does. It increases the percentage of correctly forecasted states by about 20%, and it increases the share of the incorrect forecast by 10%. So it means that on average we get 70% of the missing states correctly forecasted, just by specifying this hierarchical prior and letting no other information. And this just shows in a way that these states are exchangeable within the census region. Now, based on these Monte Carlo simulations, or Markov chain Monte Carlo simulations, I can also use the formulas that I showed you earlier to generate uncertainty around the forecasts. So they give me the probability that the Democratic candidate will win. In this case, I just show you the results for the 2012 election, and the graph shows that in Illinois it was the most certain state for a Democratic victory according to the model, and Utah was the least uncertain with maybe, I don't know, 4% chance that the Democrats will win this case. So in this case, most of the results are far away from the 50% line, but of course they could also cluster more closely to the 50% line, which would mean that probably the forecasts are very uncertain in the states, but then also at the national level, because I'm not sure which candidate will win that state. Let's move on to the national level. And first of all, I mean, this is just a binary case, so what I do is I forecast which candidate will win the state, then I allocate the electoral votes of that state to that candidate, and then I sum over all the states, and I predict the candidate to win who wins more than half of the total number of electoral votes. That's the simple way of the standard model. It shows here for the 11 elections that it gets it right in 8 out of these 9 elections. The only case where it gets this wrong is 1980, where the model predicts a re-election of Carter. The main motivation for me to try the hierarchical model was that I couldn't produce a forecast for 1976 and for 2004, just because according to the model, none of the candidates would win more than half of the electoral votes. Mainly because there were no respondents in the other states. And then I wondered, yeah, but I mean, there must be something I can say about these elections. And specifying the hierarchical model at least allows me to make a forecast in these 2 elections. In 1976, the forecast is correct. In 2004, the forecast is incorrect. And it still gets the election of 1980 wrong. However, I mean, I did not really expect that it would increase the forecasting accuracy in these cases. It's mainly that it allows to say, well, this is a really uncertain election for the model, and I don't really know which one is going to win. So for me, the key point in this case is that it allows to generate posterior certainty that the Democrats will win the presidency or the Republicans. So all this is doing is 1,000 times, based on the inferential and predictive uncertainty, to allocate the electoral votes and then to sum them up. So each of these densities is the distribution that I get for each party of the electoral votes, and the vertical lines indicate the actual results. And for instance, in 1980, the model says, well, it's really 50-50 whether Carter or Reagan wins the election. In 1976, where I get it right, it's 61% certain that Carter will win it. I'm not sure I would bet a lot of money based on this forecast. In 2004, again, where the forecast is incorrect, but it comes with a lot of uncertainty, and it basically again says it's 50-50. But if forced to make a forecast, it would say in a way that Kerry would win the election. The last thing I would like to highlight is that since 1992, the mode of the distribution is fairly close always to the actual result. I think before the elections, the mean absolute, or the mean, what did I calculate? I think the mean squared error was around 200, if I'm not mistaken. If it's closer to there, I think it's about 40. So for some reason, it seems that landslides become less common since 1992. And since then, it's a fairly good predictor, but I would need to explore more whether this is just a result by chance or whether there's anything substantial behind these convergences between the actual and the predicted result. So let me just wrap up. What this paper does is to propose a general method to make citizen forecasting even better. It does so by specifying a hierarchical model of citizen forecast, which allows us to account for inferential and predictive uncertainty, which is very important in communicating the results. And finally, it provides also a statistical framework for generating predictions where nobody or no respondent has been interviewed in the state. So in a way, I'm not saying that I would still argue that it would be nice if future surveys could interview people in these states, because of course this would generate better predictions than my statistical model here. But if in case that's not available or not possible, at least there's one way that improves the accuracy without having to interview more citizens. The next steps I'm working on is to check the calibration of the certainty. Of course, it's easy to say, well, I'm 70% certain that Democrats will win. What you would like to see probably is then, yes, in the end, when I make a statement like this in 7 out of 10 of these cases, I get it right. You don't want me to be underconfident or overconfident, so I would need to figure out a way out to calibrate these statements. So far, I haven't included time in any way, so there's just an analysis of one election after the other without pooling them or without generating, I don't know, an auto-regressive process or anything. There might be still some leeway I can use to make it even better. And another possibility is that it's straightforward in this multi-level model to include individual as well as aggregate state level predictors. For instance, it might be, or have another paper where I show that you can estimate the competence of people, and you can weight people by their competence in an optimal way, and you can also in a way delegate the forecast to the most competent members. So these are possible extensions of this hierarchical model, but at least this is already the broad framework for that. And this brings me to the end of my presentation. Thank you.
Okay, my presentation is actually quite related to presentation done by Professor Stephen Fisher. So my paper is also deals with polling errors, but from the perspective of total survey errors. So, okay, so let me start with one question for you. So the question is, okay, a perfect random, simple random sampling poll shows that 48% of people will vote for candidate A, just one day before election. Then what will be your guess about the real voter share of that candidate? Like 48%. Then what will be your guess? Do you think to see 58% is quite normal, or is quite outlier? So my question is actually to see 58% is actual vote share is not that rare thing. And the reason is this. So when we talk about survey error, actually many people just think about sampling error. So the most widely used concept of survey error is actually margin of error, which is just based on sampling size. However, here's a big question is, we know that there is non-sampling errors, right? So here's the big question is, if we really want to use this concept, we have to assume that most of survey error comes from sampling error. And is this correct assumption or not? And my answer, and actually I think most public opinion experts will say actually the answer is no. And we have actually one paradigm or one framework which is called total survey error. This paradigm says basically, okay, as we know, survey error is composed of sampling and non-sampling error. However, most of survey error can be explained by non-sampling error. They say 80% or even 90% of survey error comes from non-sampling error sources. Also, they say when we talk about non-sampling error, many people think it's like a systematic error, means bias. So basically, we say okay, one polling organization overestimate the public support for a candidate or underestimate. No. Total survey error approach says even the random error part of the survey is heavily dominated by non-sampling error. So what this means is even the variance of a polling estimate is largely determined by non-sampling error. So one big assumption, implication of this approach is the current methods used to estimate underlying actual public opinion is seriously flawed. Why? Because all these methods assume that sampling size is the most important factor in determining the polling accuracy, including Gen-1 methods. So basically, they say they use a dynamic linear model or dynamic latent variable model or common filtering. But if you look at their models, what is the most important factor? What determines the precision parameter in the common filtering? Sampling size. Means a poll having a bigger sample is more accurate than a poll with smaller sample. However, what this assumes is sampling size or sampling error determines the survey error. But as I told you, TSE says no. Non-sampling error is much bigger than the sampling error, even for variance of survey error. So what this means is we should not use sampling size to determine the size of survey error or even in estimating the underlying public opinions. Okay? So in this paper, we try to propose, actually not propose, we try to introduce a new method which is called a dynamic factor model, which is developed by econometricians, and to measure underlying real public opinion. Okay, so then why we need these methods and how this is different. Okay, let me just pick up the most advanced and most popular model in estimating underlying public opinion, which is common filtering. Common filtering is a univariate time system method. Means it's kind of simple regressions. It has just one observation. However, this dynamic factor dynamic factor model is multivariate time series method, like a VAR or data error collection. Means dynamic factor model use state space form, like common filtering. However, in common filtering, this YT represents what? Just one observation, one pole. However, in dynamic factor model, this YT represents a vector of observations, means multiple observations, multiple polls conducted at the same time period. Okay, so this is a big difference. And the idea is something like this. Okay, we have like a public opinion on some time period T. However, in the case of presidential election polls, many companies, they conducted their poll almost on daily basis. So what that means is we have actually multiple observations for one underlying real public opinion. And why don't we want to make use of this multiple observation, which is quite correlated to each other. Also, the other thing is this multiple, okay, let's say there's a public opinion, real public opinion trend like this. And there is a multiple polls like this. They move like this. Each poll should be heavily influenced by or determined by the underlying real public opinion, right? So each poll should be composed of actual public opinion plus measurement error or survey error. Okay, so it should have two components. And dynamic factor analysis says basically, okay, that means this multiple observations shares the common things, and it has its own very specific error component. And this means factor analysis. So in one word, dynamic factor analysis is time series version of factor analysis. If you know about factor analysis, then you think I think you will think dynamic factor analysis is actually a pretty good way to uncover that underlying public opinions. Okay, so this is a really big difference. Also, the other big difference is dynamic factor model does not use sample size for anything because it does not believe that like a poll having a bigger sample size is more accurate. Okay, okay, this is very widely used by economics, and all these are big economists, big econometrician names, and something like that. So our strategy here is we use dynamic factor models with the 2012 presidential election polls, and we estimate the underlying true public opinion, and then we measure the distance from each pole and the underlying true public opinion, and we measure that distance as a survey errors, and then we calculate bias and variance of each pole. Okay, this sounds good to you? Okay, so that's what we did. Okay, here is how each poll performed in 2012. As you can see, this represents the ratio between support for Obama and Romney. So one represents the support for two candidates are tied. And this represents basically the support for Romney. So this means actually the support for Romney is not as high as support for Obama. Okay, as you can see here. And there are many polls like this. And this is dynamic factor model estimate of the underlying public opinion. And then we measure this distance and consider this distance as a survey error. Okay. So result is something like this. So basically, we know that there's two different kinds of polling error. One is systematic error, which is also called as bias. The other one is variance, the same of the standard deviations. And we measure the bias of each poll and standard deviation or variance of each poll. And then we calculated the mean square error, which is bias squared plus variance. And what we found is bias actually explains 2/3 of total survey error in terms of mean squared error. So we verified that, in fact, as TSE insists, the non-sampling error largely accounts for the survey error. And the other actually very important thing is this one. This graph represents the standard deviation on y-axis, and on x-axis is represents sample size. Well, actually we learned simple regression. We found that there is a positive relationship, significant positive relationship between sample size and the size of standard deviation. What this means is if one poll has a bigger sample size, it's more likely to fluctuate, which does not make sense if there's only sampling error exists. So how we can explain this? Actually, let me say, but we got a significant coefficient. However, the R-square was like a 0.09 or something. So I think basically there's no relationship between these two things. So here's what we can infer is sample size even does not have, and maybe has very little impact on even the variance or fluctuation of polls. So this, I think this is another actually big evidence for total survey error paradigm. Means non-sampling error not just determine the size of bias or systematic errors, but it also has a very big impact on the variance of the survey errors. So as you can see, we cannot find any evidence that polls having bigger sample size has a smaller standard deviation. Okay, so that's our major findings, and I think I'm short of time, so let me just jump on the conclusion. The conclusion is something like this. Where TSE, total survey error, is actually the dominant view of the polls among the pollsters. However, there are very few empirical studies verifying the TSE approach is correct. As far as I know, there are only 2 empirical studies showing that non-sampling errors largely accounts for the survey error. However, these two empirical studies based on company-wide experimental polls. And our analysis here is, as far as we know, the first analysis using nationwide polls conducted by major polling companies. Also, in many cases, we are interested in this nationwide poll conducted by major polling companies, not like a company-wide or experimental poll. So I think the one contribution of this paper is we just verified empirically that TSA approach works very well with even these nationwide polls. And another practical implication for polling company is because polling accuracy is not so much influenced by the sample size. The polling company, they do not try to increase their sample size, especially just before elections. Why I'm talking about this is many polling organizations, they increase their sampling size just before election because they want to have more accurate predictions. However, Gallup used like a 3,000 sample size, but in 2012, Gallup gave us the worst prediction about the election result. We can find this kind of examples a lot. So one implication for polling organization is polling organization or polling company, they can spend their money to collect more people or to increase their sample size, or they can try to reduce their non-sampling error sources. And the implication of our analysis is polling companies should use their money to reduce their non-sampling error sources. And the other general implication for public opinion study is this. Public opinion may look like more volatile than real public opinion, simply because of non-sampling errors. Many people talking about whether the public is rational or public opinion is volatile or is very stable. When people talk about this, actually people just think about marginal errors, just sampling errors. So, well, one of the arguments made by Jala is, if they are rational and their opinion is stable, then how we can find this 10% change from one pole to the other pole? When he talk about this, he just think about sampling errors and marginal errors. He think like when we have like 1,000 sampling size, the 95% confidence interval should be plus minus 3%. But here we have like a 12% change from one pole to another pole. So public opinion must be very unstable. Well, maybe public opinion more stable than he thinks, but it may look like a very fluctuate not because people change their minds randomly, but because of maybe there are big non-sampling errors. Okay, that's it.